Hello, everyone. Welcome to the Electrical Systems Design webinar, hosted by Cornell University Autonomous Underwater Vehicle Team. We're going to take a little break just to make sure that the sound is working. Please bear with us.
It's live now, so I'm going to be able to hear it for 30 seconds.
Okay, so let's get started. So today I'm going to be talking a little bit about kind of how to break down the competition to decide what electrical components you need. And then once you've decided which tasks you want to accomplish, then going on and choosing the correct parts, which involves choosing whether you want to do a custom or you want to just go straight off the shelf components, both of which work perfectly fine. And then in the end, I'll just kind of do a recap. And if you have any questions, definitely shoot me an email. My contact information, msh276@cornell.edu. So yes, feel free to send me emails throughout the webinar, and I'll be sure to answer them by the end. Okay. So first is how to break down the competition. So Dave always gives us lots of tasks to do, and at least for me, and feel free to have your own opinion, there are four main different types of tasks. You have vision, which is such as the pipe tracking, buoy, which requires a lot of software, good cameras to detect like the correct colors, correct shapes. And then the next one would be fine manipulation and actuation, which requires slightly more hardware. You'll have such as your forward manipulator, your recovery, bins, torpedoes. For us, we'll use some combination of motors and solenoids in order to accomplish all of these different tasks. Next is strictly vehicle control, which requires good thrusters, good control system from your software subteam. This includes like your circumnavigation task and really just being able to get between different mission elements. And then finally is your hydrophones, which is, it's a very unique task where they have some kind of pinger in the water and you need to be able to provide your own hardware and software solutions to be able to track it. So yeah. So first off, the hardest part is really choosing which tasks to attempt, because at least for our team, we try to attempt basically everything. But looking at the fact that we've been around for close to 15 years, we've had lots of time to experiment. Our team has grown to a size of about 40 people. Our electrical team is about 10. So really taking all of that into account, it's fairly easy for us to kind of divvy up tasks and say, hey, you're working on a motor controller, you're working on power distribution. For smaller teams, really it comes down to just kind of deciding. If we look back at like our mission from 10 years ago, our main objective was to basically see a buoy, track a pipe. And I think this was before we had a DVL. So that's another thing to consider. So really choosing what you think is manageable for your team, given test time, given team size. So now I'm going to break into a section about how do I actually choose the part that's right for the team. There's always trade-offs between performance, complexity, cost. So I guess the first one I'm going into is choosing the type of motor. In the past, we've actually stuck to brushed DC motors. And brushed DC is actually a good place to start because control-wise, it's very easy to implement. You use basically an H bridge, you PWM a signal to it, and it's pretty easy to implement. As far as performance-wise, moving on to like a brushless DC motor would actually be a little better. It is maybe 10% more efficient than a brushed DC, and it gives you pretty good speed control. Cost-wise, I would say they're probably comparable. So we're actually moving to kind of a brushed DC solution, hopefully to kind of help with our controls a little bit and give us a wider range of like speed control. And then comes to, oh, so those two types of motors we use mainly for um, just driving and driving between tasks and really control of our overall vehicle. If you want more fine control, you can use, or things that we've looked into are stepper motors or servo motors. The difference being a stepper motor will give you relative positioning. It'll move by incremental steps. And in order to hold a position, you need to constantly apply power to it. In order to kind of get around, or depending on the application that you're using, say you don't want to be constantly applying power to it, you could add something such as an absolute encoder in order for you to um, be able to return the stepper motor to a specific position. Or you could have some kind of mechanical solution, such as like a block, which says, I'll reset my stepper motor to this position, and then always go reference to that. That's a couple of things we've thought of in the past. In addition, or kind of on the other side, you have your servo motor, which basically you give it a signal to tell it an absolute position to orient itself to, and it'll hold its position. So kind of looking between those two. We've looked at steppers in the past just because then you get that nice like incremental. However, both are perfectly reasonable solutions. Okay. The next big debate that we have is what type of camera to get. And so you'll hear the term CCD and CMOS quite frequently. And there are a lot of great resources on the internet to look up if you have any questions about it. So kind of the biggest difference between the two would be looking at CCD is always a global shutter type of camera. CMOS, you can get either or. For a global shutter, it basically will take an image and expose the entire frame at once. So you'll see, so basically you'll be collecting light for across the entire frame as long as like the shutter is open, versus a rolling shutter will update kind of how it sounds, like from the top to the bottom or left to right. And both kind of introduce interesting problems. So the main problem rolling shutter, which is, as I said, typically CMOS cameras, is you have to deal with skew and wobble, which basically means that if there's a lot of movement when you're trying to collect the image, then you'll kind of see it distorting the image slightly. Versus if you're using a CCD camera, because it collects the light all at once, it's a little bit less of a problem. So you won't have like, say you're taking a picture of like a pipe and you're slowly drifting, you would see the pipe sort of change heading basically. And that could cause problems when you're trying to navigate towards the next task. If you're using a global shutter, basically you could see the image smear across the screen, but you wouldn't see it like change direction. Smear is also in the sense of if you're in a dark place and you're looking directly at a light, you'll see those strange artifacts due to, or the pixel streaks across the screen. Sorry. And that is more commonly found in CCD cameras than in CMOS. So really just deciding on the trade-offs between the two. At least for our team, I believe we use CCD cameras. So if you have any questions about like the specific models we're using, definitely shoot me an email. Okay. The next one is what I call 2DVL or not to DVL. So really, as you've probably heard, DVLs are a great asset to have on the team, as they allow you to have pretty accurate positioning in the water. And it allows you to kind of know if you're starting to drift. So say you can see something with your camera, but as soon as you zoom in and get really close to the object, sometimes you lose vision and you start drifting. And it's more likely that you will miss your target or have just strange complications. Maybe you're trying to find you're following a pipe, you're trying to find your next task, and you're relying on your camera to kick in, which is only visible up to a certain range. So sometimes you'll kind of be off your mark, and it's will take much longer to kind of find where you are, do your search algorithms. Therefore, having a DVL is a great asset. The main problem is cost, and I know a lot of teams have trouble with this, especially new teams. And really, a DVL will run for a few grand. My recommendation would be to really seek sponsorship for this. Um, if you have the budget for it, we got a pretty good sponsorship with Teledyne, and it kind of allows us to purchase it maybe once every 5 to 10 years, as our budget permits. Another kind of option to look into is talking to the company about either getting something used, or something that's of an older model, or potentially looking at rentals, which could come out to a reduced cost. Um, so, yeah, there's really, yeah, and then there's always the challenge of kind of integrating the sensor into your system. Really, just having a DVL isn't gonna like make it effective in competition. You need to really sit down, make sure that you're interfacing correctly, the data you're getting is usable, and that really comes in on the software side. Okay, and then another task that we kind of faced on the electrical team is interfacing with other subteams, because electrical is kind of that realm between hardware and software. So some big some big things to consider are when you're dealing with your mechanical system, knowing where my parts going to be. Um, for example, if you're putting your compass near your computer, near thrusters, you could be very prone to noise, and making sure that you have the proper magnetic isolation that you need. Um, Also, as far as just interconnects, making sure that there's enough space to fit all of this cabling, because we do a lot of custom solutions. We deal a lot with wires going everywhere, wires between boards. If you're doing off the shelf, then a lot of the store-bought connectors that you're going to get don't necessarily have the proper bend radius that you need. So making sure that like all of that fits into the mechanical design. Um, as far as external connections, I mean things such as we use CCOD in order to interface because it's a really good waterproof connector. Oh, sorry. It's a really good waterproof connector that is really easy to use. Usually they're kind of big, but recently we've been moving more to the Hummer series, which is much smaller. And we have a lot of external connections going to our thrusters, going to our camera, our hydrophones enclosure, valve enclosures, and just making sure that all of that still fits in the mechanical design. On the other hand, we do need to be able to interface with software. As we have, so because we do a lot of like embedded systems work, we need to make sure that whatever registers that we're passing to our software is accessible, is easy to use, and yep, fits kind of nicely into the software system as well. So make sure that whenever you're designing something, whether you're using a different protocol, or you are designing, like how is software going to access my board? Say I'm running a thruster controller. Am I going to ask them to give me a PWM value? Am I going to ask them to give me a speed value? And making sure that your software team knows exactly what your board does. Okay, now I'm going to enter into the custom versus off the shelf. And as I've mentioned before, our team does a lot of custom solutions because we do have the manpower for it. As far as off the shelf components, you want to make sure, well, there are a lot of good off the shelf components that you can get, and there are a lot of trade offs between the two. We actually kind of use a combination of the two, but do implement a lot of custom solutions. So here on this table, the first I've said is tunability versus reliability. So the nice thing about custom solutions is saying that, say you have a certain threshold for a component. So for example, if you were doing a battery discharge, if you were doing off the shelf, it had very strict, if you're below 3.3 or something like that, it'll shut off everything. Versus on a custom solution, you can look at it, you can monitor like, hey, this threshold isn't necessarily appropriate for the team, or I still want to be able to interface with the pack when we are below this, so I can do a recovery charge, so I can just kind of still work with the pack, not necessarily discharge, but just to kind of see what's still going on. Custom solutions allow you to do that. So a lot of tunability in there, but really you got to make sure that whatever you're doing is still safe. On the flip side, you have off-the-shelf reliability, which means that companies have large teams of people and they've tested it extensively. They know as soon as you get it, it will hopefully work. Make sure to double check your data sheets. Talk to the companies if you have any questions, something seems ambiguous, because sometimes off-the-shelf components won't interface as easily into your system as you might think. Or, for example, if you need some kind of software package or something in order to make it run, you have to make sure that you have all of that included. The next point is when you're implementing custom, it is more complex design work, because what you're basically doing is taking a little processor of your own and you're interfacing with all of the hardware that you need. So when I say custom, I mean you're using certain ICs, such as like ADCs, you're not going to implement yourself, DC-DCs. But when it comes to building like H bridges, whether or not you make that custom will add to the level of complexity, choosing the correct components, doing current calculations, running simulations. For off-the-shelf design, design work will be a little bit less complex on the hardware side, but it would be more complex on the integration side. So making sure that your software team can actually use the part that you've designed for. And again, make sure whether or not using custom or off the shelf that you save a lot of time for testing, a lot of time for integration, because really that has always been a very challenging part for our team, just to make sure that everything is communicating properly and working together as it should. And then finally, it's kind of, again, comes down to compromises. It's the amount of time you want to put in, the experience you want to get out of it. So again, because we have an electrical team of about 10 people, we're able to break down our electrical system into different categories, which I'll go into a little bit more later, and then really design for the different areas that we want to achieve. So we want to implement current sensing, we want to monitor voltages, we want to save some information on an SD card and read it back later. We are able to design for that just because the manpower really helps us. Off the shelf is a good compromise. For example, last year we needed a PoE injector. We didn't have time to make it ourselves, and we thought we can fit it, let's use it. So it worked really well for us, but we had to compromise on size. This year we're trying to integrate it hopefully into our system so we can make it a little bit more compact, but then we run the risk of, will it work, will it not work? So really just kind of making your design kind of robust to changes. And then finally, cost. So that is a big deal for both categories. It basically depends on which project you're working on, for whether or not custom or off the shelf is cheaper. Usually, I don't know, it kind of depends. So if you're trying to integrate kind of an off-the-shelf component into your design, sometimes you can get a part made for the exact same cost, but maybe the functionality is a little different. So, and sorry, let's take a step back. So, sometimes off-the-shelf components will implement a lot of things that you won't end up using, a lot of functionality that you're paying for but don't necessarily need. And custom, you can kind of get rid of that intricacy while still maintaining like the functionality that you need in order to run your system. Sorry, that was kind of vague. I will get more into that as soon as I talk about a little bit more about our system. Okay, so moving on to kind of how our team will implement like the design or the electrical design for the vehicle. So going into our subsystem breakdown, we have 4 main subsystems. We have our power subteam, which will handle all the power distribution throughout the vehicle. We have our mechatronics, which will handle anything that's moving, basically. Our sensor subteam, we have quite a wide range, or we have a pretty large sensor suite, and making sure that everything's talking correctly, and then implementing some custom sensors. And then our acoustic subteam, which handles the hydrophones task as well as a few other fun projects that we're working on. I've listed a couple of webinars coming up. If you have more questions about making design from scratch and then implementations on the hydrophone system. So check those out. Okay, so first off is our power system. So we run off of 2 LiPo batteries, and I've listed our sponsors here. So Advanced Energy we use kind of, last year we used it as kind of our primary battery. What's great about them is we sat down with them. They allowed us to kind of give them dimensions, give them capacity, and they kind of made the pack that would work best into our system. Just kind of a disclaimer, lithium polymer batteries are fairly expensive. So yeah, that's always something to keep in mind is, again, cost. And then max amps we use because they have a really great variety, high capacity, high quality, and usually they sell it for slightly more reasonable, but again, it's still pretty expensive. And then from there, we have our battery management board, which will look at cell voltages and charge capacity, and will let us know if we are discharging our packs correctly and safely, and then make sure that over time, how well is our battery performing. So basically, we implement all of this directly using cell buffering and ADCs, some off-the-shelf solutions, which would still require some IC embedded work, would be basically a fuel gauge IC or battery management chip, both of which will monitor your voltages, your currents, temperature. But yeah, it ultimately will involve some software interfacing in order to actually use those chips. A lot of teams will just use the battery pack directly, and that is perfectly fine. Just make sure that whatever you're doing, you're not over discharging your battery, because lipos, for example, are extremely volatile if you misuse them. So got to watch the clock on that and make sure that you're being safe. For our power distribution board, it basically takes in the input from our batteries. It'll use DC-DCs for all of, in order to create the voltage rails for various sensors, 24, 12, and 5 volts. The nice thing about using DC-DCs is you come out with a more stable output, whereas the battery output voltage will change anywhere from 22.8-ish to 25.2. So some sensors will require a more fixed range of voltages. For example, the computer we were using last year could only handle a plus or minus 0.6 volt kind of ripple noise sitting on our 12 volt output. So had we directly connected this to like a 12 volt battery, then our computer would fluctuate between being on and off. So also DC-DCs are quite stable. Yeah. And in addition, we do some isolation on the board to kind of protect the noisier components, the not noisy components from the noisier ones, such as thrusters, and yeah, cool. And then we implement little things such as current sensing, the ability to kind of toggle each channel on and off, say we need to reset a specific sensor. Our next subteam is our Mechatronics subteam. As I said, this handles all of our moving components. So our thruster controller handles the main driving thrusters on the vehicle. So as I said before, we're now making the switch from brush to brushless, which we're hoping goes well. We're still making custom H bridges. Kind of a trade-off here is that for a brushed controller, you would need one H bridge. For a brushless, you need 3 half H bridges. And really just the size constraints are a little different. Control for brushless is much harder. Because you need proper timing, you need to know basically the position of your motor at any time. So on this board, we will implement things such as H bridges, isolation, as I mentioned before, just to kind of keep the rest of our electronics safe in case a thruster just stops working and it sends this huge spike of current back on our plane. And then current monitoring. There are a lot of great off-the-shelf solutions for motor controllers, and don't feel like you have to implement it yourself. What we like is by making it custom, we're allowed to kind of choose, here is the amount of current that we can provide, and really you can swap out certain components without replacing the entire chip. It's not cheaper per se, but it is more customizable. And it also gives us the high current specs that we need. As far as stepper motors go, so very similar to our main thruster controller, we're implementing the stepper motor with custom H bridges, isolation, the control and logic we implement on board using our own microcontrollers. And in order to get rid of the earlier kind of concern that I mentioned before about stepper motors only having the relative positioning, we've added an absolute position encoder. Again, an alternative is to use a servo motor, and you in no way need to build a controller from scratch. But again, it allows you to kind of set different tolerancing and make sure that it really fits into your design well. And then finally, in our Mechatronics team, we have our actuator board, which basically will drive our pneumatic solenoids and our DC motors for our forward manipulation task or any kind of new challenges that come up. So it's kind of an all-purpose board, but it is very useful for us. And then it'll also interface with our kill switch. Okay, our next subteam is sensors. And we have quite an elaborate sensor suite, complete with IMUs, compasses, our DVL cameras, just remember that if you're using anything that you get from companies, that it fits well into your system. If it's talking over serial, you have either the necessary protocol to interface with it or kind of retrieve the information, find out if it's spewing raw data values at you or if it does some kind of filtering on its own. And yeah, just make sure that, you do a lot of testing. The three things listed at the bottom are actually the custom boards that we make. So we have a serial board, which we need an outstanding number of serial channels. I think last year we clocked in at 14. So we basically take one USB from the computer, we split that into 14 serial channels, and that's how we communicate with all of our sensors. Our HIM board, which is heading and inertial measurement, we have an IMU and a magnetometer from SparkFun that we actually put on a board. They communicate over I2C, but we do some processing on our microcontroller and we talk back over serial. And then our GPIO board, which has an ADC, a DAC on it in case we need to add anything. So we've mainly used it for pressure and depth sensing and really adding just any of these small projects that we kind of need. We want to make them smaller. We want to move away from off-the-shelf components or anything like that. And this point that I've put at the bottom, sponsorship is your best friend, which is very true when it comes to sensors. So, for example, as I've mentioned before, like our DVL is not something that we can afford just to buy one every year. And we can, as far as affording it at retail price is very difficult for us. So working closely with sponsors, kind of telling them, the benefits of sponsoring the team and your team specifically, and I guess the competition as a whole. So if you are interested in learning more about sponsorship, check out the sponsorship webinar. As far as cameras, we also get a great discount on those. Some of the sensors, companies have been really generous. They give us sensors to kind of play with. So I know a lot of teams have recently received the P&I tracks. And yep, just kind of integrating that in your system. And what they really want are people to try out the sensors, give them feedback about how the sensor performs, what they can do to improve it. So really talking to companies about that is a great way to kind of get your hands on sensors like that. Or if you're making a custom sensor solution, I believe we're building them for about $30. So, or as far as like the HIM board and such. Okay, and finally, our Acoustics subteam. So, as you know, there is the hydrophones task, where there is a pinger in the water, and we need to be able to detect where it is and be able to navigate towards it. That requires a lot of onboard signal processing. And now we've made the decision to do all of our processing on an external board and then relay that information back to the computer. If your computer has the processing power for it and you want to send just raw information to it, that is also a viable solution. Again, if you have more or questions about how our hydrophone system works specifically, check out our webinar on November 29th. And then another project that we're working on is a custom pinger. So the pinger that we use currently, we actually get from a company, and they let us take it out for months at a time and just kind of play and test our hydrophone system with it. This custom pinger would hopefully allow us to both transmit at like the desired frequencies as well as receive commands so that we can kind of adjust what frequency we're transmitting at. Okay, so this is basically my last slide. It's going to be just a general recap of everything I've talked about. So if your team is brand new or you've only been in the competition for a couple of years, really what it comes down to is first determining what tasks are kind of viable for your team. So looking at sensor limitations. When I say requirements, I mean, like, do you have a DVL or not? Is it really feasible to spend all this time on a search algorithm trying to find a task, or to focus on a couple and do them really well? Oh, just kind of the trade-offs there. Just knowing like what you're doing. Really a good idea to do custom? Should we do kind of off-the-shelf components and then kind of work our way into custom? And then integration time and debugging. Definitely save as much time as possible for this. Even after we get our vehicle in water, we spend a couple months just making sure that everything is working at its finest, and making sure that, hey, we didn't realize on the bench, but maybe we've soldered something a little poorly and now it's starting to act up when we're trying to run our thrusters at full speed, or if something strange happens on our system. And really just strange bugs that you'll only see from testing. And then secondly, once you have kind of like that high level, what do you want the vehicle to do? Then you break it down into specific tasks. So, for example, if you're going to be running a buoy mission, what do you need to make that happen? So you're probably going to need a battery. You're probably going to need some kind of computer, camera, thrusters in order to drive there. And then now that, say, for example, I'm taking a thruster, what type will work best for me? So let's say we're using a brushed DC motor. How will I control it? How will it interface with the computer? And kind of how am I going to get this integrated into my system? And then third, kind of building off of that, is our custom solutions right for me? And we do not use custom solutions for everything. And it's a very large system to kind of integrate. So making sure that all the pieces are working properly, and really choosing which parts you want to make custom and which parts you're fine getting off the shelf. So lastly, I've included our webinar schedule one last time. Next time we'll be talking about kind of, if you want to make a custom board, how do I get started? And going into more specifics about the overall design, and then layout, getting boards printed, soldering. And then finally, we have our hydrophones how-to, where we'll be discussing kind of how we implement our hydrophone system and how other teams have found an approach to hydrophones. There's really no correct solution, but some are easier to implement than others. So that is about it. If you guys have any questions for me, feel free to send them out. They are, questions I will be taking. Remember, my email is msh276@cornell.edu. Okay, so I've just received a question asking about how our team does wiring. It's easy to pick out wiring when you see it in a store and determine its flexibility, strength, quality of the shroud, but it's hard to determine these qualities when ordering online. Where do you buy from? Any recommended companies? So from what I understand, this question is asking not wiring within the sub, but wiring from basically our upper hull pressure vehicle to all of our external enclosures. So we mainly use Seacon, and part of the reason is because they give us a really good sponsorship. The other reason is because it's a really great waterproof connector. So what we've been using is it's looking between either using wet mate versus dry mate. And wet mate will tell you that you can basically plug it in underwater. And we typically use this for things that, such as batteries, where you really want to avoid having like a power ground short when you're trying to swap it out. And because we try to design our system to be hot swappable, which means that we can change out batteries while the vehicle's still live, that having that wet mate solution is a really great safety precaution. It's not power cycling our vehicle. Versus dry mate, which are things that you typically wouldn't be unplugging underwater. And usually those connectors are a lot smaller. So again, another trade-off there. So yeah, that's my recommendation. We use CCON for our underwater cabling. If you need specific cables, such as like underwater USB solutions, or like, I don't know, anything like that, definitely look around. If you have any recommendations, I guess reply to this video. Okay, so we have another question about the serial board that we're making. So the question is, how do we implement communication with the computer using 14 serial channels, basically? So what we're kind of doing is, as you've mentioned, we're using basically multiple channel FTDI chips. And FTDI is really great because they're one of the few companies that will actually take like a USB signal in and provide multiple UART outputs. So basically what we're doing is we're taking a multiple port hub, taking in the single USB, splitting it into multiple USB channels, and then using a multiple channel FTDI chip. In the past, we've used 2 and 4. It kind of depends on the number of channels you need. And then basically splitting it into, or level shifting into serial channels from there. One thing we're actually looking into this year is like in automotive design, you would typically, or you would see a lot of people using a CAN bus, which basically means that you can all communicate over a single line. It's kind of a nice alternative. You don't need one serial channel per device. But at least for us, it'll be a challenge as we have to write all the protocols for that. So things to look into. Okay, so yeah. Okay, so sorry, let me go back to the wiring question because I think I was confused at the time. For wiring within the hull, the question is a tiny bit confusing, but let's see if I can answer it properly. So when it comes to wiring within the hull, we basically look at, well, because we do a lot of like CCON connections, they come with, I believe, like 20 gauge, 2022. And so we will wire our CCON, those wires to like our boards through Molex connectors. And as far as routing goes, we're trying a thing with last year, or in the previous years, we've been trying to integrate like a backplane so that all of our boards will interface in one direction to our CCON, and it'll make sure that we don't have like wires going everywhere. We can kind of keep the connections between boards to a minimum, and that way our boards are more easily accessible. So it's kind of the concept of a backplane, as we call it. So basically doing all of your wiring connections from one side, and then boards plug into the other side. And that way it keeps the system really clean, keeps the wires free. Something that Team Sonia has been doing is making like a integrated PCB backplane, which is really cool, keeps the wires out of the way. We're hopefully trying to work towards something like that this year. And we'll let you know how it goes. Hopefully that'll keep the wiring down a little. I hope that answered your question. As far as wire management goes, and routing, you just got to make sure that in your mechanical system that they've accounted for that. So if you know approximately how many wires you have, you know how much space you need in order to route it from your end cap to your boards. And then that always brings up a good point of board placement in the vehicle. So making sure that if board A connects to board B, they're not like across the vehicle from each other, because then the wiring gets really messy. You want to have them, hopefully you keep them kind of close together. The way we handle this is we have a dedicated pressure vessel that handles all of our custom electronics. We put them pretty close together. That way, when we're wiring board-to-board connections, then we can keep the wires kind of short and hopefully as clean as possible. Okay, if there aren't any more questions, then I think I will sign off. But again, if you guys have any questions for me, definitely feel free to send me an email, and I will try to get back to you as soon as possible. In addition, check out our future webinars if you want to find out any more information about either custom board solutions or our hydrophone system. Thanks for coming.